As a reminder, there is a poll everywhere live if you want to log on, and while we're all sort of still filtering in, also shout out. We're officially in week 2 and there's still a sizable number of people in person. I'm proud of you, y'all. I understand. So today we are going to try and wrap up some of the conversation we started last week. And we are going to start a whole new conversation that I promised y'all about some more mathy natures of things, but hopefully it'll feel positive. I wanted to pick back up where we left off and just wrap up that design discussion conversation. So we had started Friday's lecture with 3 possible scenarios. And in those scenarios, we knew we were going to use something called the list ADT. And remember, the list ADT, the abstract data type ADT, is that sort of conceptual explanation. A list is an ordered series of elements in which you can insert and append and find at an index. And you could implement that with either an array or a series of nodes. Now, actually, we are going to, throughout the rest of the quarter, pick up a bunch more ADTs and actually a bunch more data structures that could go under the hood. But for right now, we're sort of at list, with list as an ADT and then just array or linked node underneath the hood. Here are some of my different explanations why one might be good in some scenarios and one might be good in other scenarios. Like I said, in this class, you will find that the correct answer is just an answer that you can justify. That's really what I'm looking for here. And when we get into our simulated assessments, what our simulated assessments are going to be are questions a lot like this, where I'm going to present to you some type of scenario and ask you to think about, as the designer of the code, what ADT is the best fit for the functionality and what data structure is the best way to implement that functionality to get our optimal results. I thought it'd be fun to see what people voted on, because we sort of talked about a little bit with the song list example, you could go either way, just to sort of make sure that we're comfortable with the scenario. So the first one was that idea of a playlist. Maybe you want to optimize for moving things around, maybe a linked structure then. Maybe you want to optimize for accessing random or something like that. The second one was a bank customer transactions. In that one, again, you have this sort of series of ordered events. Maybe you want to use an array list to get specific transactions at a specific moment in time. Maybe you want to use a linked list if you want to optimize for adding transactions. The third scenario was if we want to store a queue for, say, an IPL or an office hours linked list. Maybe that's optimized for adding and removing from a structure. It's a little easier to add people coming into the queue, easier to sort of take them out of the front. Or array list, maybe you're optimizing for, hey, it's easy, right, in that linked list structure to add to the front because we have a pointer to front. If we wanted to add to the back, we'd have to loop all the way to the back kind of thing. Array list, maybe it's easier to add to the back. But I just wanted to remind you what those scenarios were, because let's take a look at what we all voted on, because we did do a poll everywhere. So here we go for situation 1, the plays list. It looks like the majority of people ended up voting array list in that one, but as you can see, not a wash, if you will. If we look at the next one, situation 2, also looks like the majority of people picked array list for the bank one as well. Like I said, if I was to probably come up with my own justifications, both of these do make sense to me. The bank one is probably a situation in which you want to have that really specific, hard to move structure. With linked lists, I don't know if you've ever accidentally dropped a node, accidentally misordered things. We definitely don't want that happening in the bank world, so maybe an array is an okay underlaying structure underneath. And then if we go to the final one, it seems like the majority of people picked linked list in the situation of the queue. And yeah, I think I could probably be convinced in that scenario that you're probably optimizing for how many people are coming and then going from the queue. And so that addition and removal operation is happening a lot more than, say, trying to access something at the middle. And so maybe the linked list is a better in that situation. Any questions about any of these things or scenarios, or anybody want to play devil's advocate or disagree with any of the things that we've sort of just discussed here as possible justifications for these designs? Cool. Yeah, okay. Well, then I want to like I said, just briefly go over some other slides before we dive into our next big topic. So if I go back and let's please send PowerPoint all of the good vibes. Why are you doing that? Oh, okay, apparently, I don't know what that was. Okay, as of course, reminder that we have our first homework assignment due this Wednesday. Also, just to give you a heads up, our first written exercise will come out this upcoming Friday. That is an individual exercise, and it will be similar to questions you may see in section. So that's why it's sort of a written exercise. Any administrative questions before I dive deeper into content for the day? Sip. All right. Okay, so like I mentioned, we've been talking about the list ADT. These ADTs, I do expect you to be somewhat familiar with already. So it's going to be a very brief review, and I very much apologize if you're like, Casey, I do not remember what a stack or queue is, but technically it was covered in 143. But this is another set of ADTs. So a stack is an ADT, meaning a conceptual description of how something should function. And the stack one is a collection of elements in which the last thing you have added to the collection is then the first thing removed. So if we think of, and I don't know, is this a very like Americana cultural touch point? And I apologize. Like I think of those like waxy, always still wet lunch trays at like elementary school, public, like cafeterias. And whenever, you know, like you had these lunch trays, they were sitting on a spring, and somebody would come out of the kitchen and they'd push a bunch of these trays and they'd like sink into that spring. And then when the person came to get a new lunch tray, you pop the first thing up off of the top, and that spring sort of shifts those things further up. And the next person's going to come grab the next thing. And then as soon as those fresh trays come out of the dishwasher, they push them back on the top, and that one on the bottom gets a little crusty because it never really makes its way to the top. You know what I'm talking about? If not, I hope this was a painful description of how we are failing the public school students of America, because boy, you should get better than square rubber pizza on crappy lunch trays, but here we are. And so you can think of other examples of the stack. It does sort of follow what we call LIFO, last in, first out. But as you can see, I'm just talking about the ordering here. I'm not talking about what goes under the hood. Let's talk about what it means to implement this under the hood with our two different data structures that we have so far. So the first one is the array implementation of a stack. So in that situation, we create an array, we push something onto the array, meaning we put it sort of at index 0 there. And then in this case, we're going to push again, and we're going to continue to fill up the array. But what's happening here is I'm going to, when I'm writing the code, I'm going to think of whatever element is currently at size -1, whatever element is currently at the index of size -1, that's the top of the stack. So when we pushed 3, that was the top, right? And the top was, you know, size, which was 1, -1. So that's when the top was at index 0. And then when we pushed again, size became 2. And so the top ended up at index 1. So the top is always at size -1, which ends up being a pretty convenient place to find the top of our stack. So then as you can imagine, whenever we want to pop something off, we just erase whatever is at top at size -1. But in actuality, if you remember from Friday, we don't really care what we're erasing. We don't actually need to remove the values. Really, then all I need to do in pop is I just have to update the size. Then I'm just going to kind of ignore what's in that spot. So, and then if I push back again, I will then update size and replace whatever is currently stored at size -1, whatever the new value is. Questions on how that works under the hood? Yes. Yes, in POP you do return numbers, so it would be something like I would access it and return it, and I'd update the size or something like that. Yes, absolutely. So let's talk, we introduced this thing called Big O analysis, again, trying to dust off some of the cobwebs. And remember that when I say Big O analysis, what I mean is, for the most part, the expected runtime, i.e. the number of instructions that are going to be executed in order to accomplish this in terms of how many things are stored in the structure. And we use the letter N to refer to that. So in this case, what is the runtime to pop something off of this stack in terms of how many things are currently stored in this array? And we learned a few different complexity classes. So there was the complexity class of constant, which means it doesn't matter how many things are in there. I don't have to look over all of them. I don't have to touch all of them. I don't have to move all of them. It's just maybe a few direct accesses of an array index. That's a constant time kind of class. Or we could have the linear class. The linear class is where I might have to go in and like touch every single thing in the array. So for example, if you remember in the array list append, if I ran out of space in the array, I'd have to make another array and then copy everything over, and that copying touches everything, so we get that linear runtime. Or there's that quadratic runtime where maybe I have like nested loops and I gotta like, for every single thing, go check everything else again. That's just sort of a reminder. So thinking of that, does anybody want to hazard a guess as to what the expected runtime of an array implemented stack pop would be? Yeah. Constant time. I love that. And let me see. Yes, I absolutely agree. And that's because we have this array index that we know it's at size -1. So I didn't have to like start at 0 and loop all the way there. I didn't have to copy anything over. So that's going to be constant time because I have that direct access to the top of the stack no matter what. Any questions on how I got to that conclusion? Constant independent event. Okay, peak for context is just the ability to look at what's at the top of the stack without removing it. So if pop is constant, what do we think peak's going to be? Constant. I agree. Size. Size is the ability to just say, hey, stack, how many things do you have stored in you? And right now I have a field variable called size that I could just spit back out at them. So what do we think the runtime of just telling them how many things in the stack is? Constant. I agree again. Is empty. That's our ability to just say, hey, is there anything left in the stack? And I have that size variable that maybe I just check if it's set to 0 or not. So is that, what do we think the runtime of that is? Constant. I love it. Aha. And then we get to the last one, the push. Does anybody want to hazard a guess at the push? Yeah. Ooh, so wouldn't it also be constant? Can you give me an example in which it will be constant? Because I do agree with you in some scenarios. Any ideas?
I think it should be always constant because you're just adding one to the size and then pushing something else to it.
Yeah, I absolutely agree. So like we saw with the 5 right there, it was sort of like there was a space. I just put that 5 in that space. I just updated 5. It didn't matter how full or not full it was. That was a constant time operation. I absolutely agree. And this is me being really annoying right now because there is a secret, what we're going to call worst case scenario that's hiding under the hood trying to sneak us into this. Let's see. Yeah. If the array is already full. That's our sneaky situation here. If the array is already full, I don't have anywhere to push the new thing into, so I got to make a new array and I got to copy everything over. And so you'll find this need to resize the array comes up under the hood of pretty much any ADT that implements it. And there's always going to be that worst case scenario that we might have to do that array growth situation. I keep saying worst case in this really annoying way because we're going to talk about best case and worst case for the rest of the quarter. And we're going to spend all of one Friday talking about it. But there is actually this idea when we're doing this analysis, both of those answers were totally correct, right? Because you could imagine what an incredibly different situation between constant time and linear runtime. And knowing when it's constant and knowing when it's linear can help us make more informed design decisions. So you'll find in industry, they tend to be pessimists. They almost always want you to think about what's the worst, what's the longest, what's the slowest this could be, what's the most memory this could take up. But actually you have a better balanced understanding of your code if you understand that, hey, you know what? For the vast majority of the time, it's going to be a constant push, except in that sneaky scenario where we have to resize the array. Questions about that piece? Yeah.
Yeah, when popping, will the array ever be shortened?
Ooh, this is a good question.
Keep the biggest size it ever has.
Thank you. Yeah, somebody asked me this after class, I want to say the other day too. I'm glad you asked it in class. So when we resize down, are we ever going to say shrink the array down? Because we talked a little bit on Friday about how that's unused memory, right? So you could imagine a scenario like, let's say it's the hour before your homework is due and that queue just exploded, right? In the IPL, and we add and add and add, and then all those TRs are just BAMPs and they're just like getting through the queue. And then after that, we just have like 2 or 3 people kind of working in the queue, but we still have this massive array. Historically and conventionally, we do not go back and resize the array down. Now, there are some situations where they expect these massive fluctuations and they might do that kind of thing. But at least for our current conventional implementations, for simplicity's sake, and because that type of I'm going to shrink down again is so rare in comparison to needing to ultimately grow, that historically we don't. But I like where your brain is at, because you could imagine, like in my little IPL scenario, you could imagine, hey, we know it's going to expand during these times, and when we know it's going to shrink down, maybe we add some type of structures in where we do shrink things down. Conventionally, no, but you can imagine in your code how you could put that to your advantage if you understand how things function. Other questions about this? Anything else? Yeah.
I'm sorry, but could you repeat like why when your array is full, you have to create a new one, why is that linear?
So that's linear because when we make a brand new array, we have the array, let's say we have an array with 4 items in it, and we make an array that's now can hold up to 8 spaces for things. We still have to go through that 4 array and copy everything over and fill up the new array, because the new array has nothing to do with the old one. And so in order to make sure that it is properly reflecting the current state of things, we first make something that's double the size, and then we go copy over the current state of the array. So there's n of 4. We copy those things over, and then we add the 5th thing kind of situation. Yes. Yes. So as you can imagine, once we get to the end of that 8 array, we double it. We make a size 16, but we got to copy over the 8 that we're filling in it, and then we make something of size 32. Yes. Multiplication tables. Great questions. Any other questions about this? Because this is very inherent to sort of like the functionality of arrays under the hood generally. Yes.
I don't know if I'm jumping the gun on this.
Sure.
But when arrays become like multi-dimensional,
Mm.
Doubling could, quadruple or.
So how do you manage this in a multi-dimensional array situation? Is that what you're asking? That's a really good question. And for that reason, it is, let's see. I can only think of one particular situation right now in which you might have a multi-dimensional array as the underlying data structure. And we might talk about it briefly later in the quarter, but you will find for the most part, very rare to have a multi-dimensional array as the underlying data structure in something like this with a list that would grow like that. More often you would say use it in an adjacency matrix for a graph, foreshadowing. The least sexy foreshadowing. But yeah, we will talk a little bit about that later. In that case, we don't do the quadrupling because actually then we know exactly how big we're going to. Okay, so there you can see linear if we have to resize, constant otherwise. We just talked about that. Okay, so let's talk about implementing a stack with nodes. We start off with a front pointer pointing to nothing. We push something in. We push something else in. We pop it off. And so we end up with this constant runtime just straight up down the line, because we're only ever making a node at the exact moment we need to make a node, and we don't have to at this moment in time loop over anything because we're always just sort of interacting with the top. That's kind of the convenient thing about the stack ADT. I don't really care how big it is. I don't care how many things are like deeper down. Like there's that crusty lunch tray that can hang out in the bottom. I don't really care how long it's there as long as there's a fresh tray at the top. And so it ends up being very constant runtime. Remember, we do take a little bit of a hit in the performance of the memory for a stack. We do take a little bit of a hit in the amount of memory that we use for the stack, but we don't have that unused memory for an array. Here's some real world scenarios. I'll let you read it. I want to, just in the interest of time, remind you of the queue ADT. They are often talked about together, the stack and the queue. They're the type of ADTs that really care about order. And so if a stack is that last in, first out, a queue is that sort of like traditional waiting line where the first person to join the line should then be the most, like the next person to get served. You can think of this as the line perhaps at a bank. And so in this situation, we need to be able to add to the back and then pull from the front, and those things kind of move. And so let's take a look at how they're implemented with an array. The way we would do this is we would say add something to the front of an array. We would add again. We would add again. So now we've got 5, 8, and 9 waiting in line at the bank. When it is time to address the next bank customer, we pull from the front. And then we kind of end up with this unused space that's both at the front and at the back of the array. So in this scenario, the big O analysis to remove something, you can see down at the bottom, see how I have actually added 2 fields? So I technically have, as you can see here, if I look at the overall state, and you can always see these in my little purple boxes here, we have a field that stores the underlying array. I have a field that stores the size, the number of items in the thing. And in this case, I have a front index and a back index. So I've added 2 extra fields because I know what's going to kind of happen is this queue is going to kind of shift about within this array based on when things are added and when things are removed. And so because I know exactly which index of the array to access in order to grab the next person in line, I don't have to go looking for it. Does anyone want to tell me what they think the runtime to remove is from a queue implemented with an array? I don't have to look for it. I just know the index right away. Let's see. Anyone else? Run sure? Yeah. Constant. I agree. Yes. Constant it is. I know exactly where to look. I don't have to loop over and find where something is. I'm keeping those indices. I'm updating the indices. Every time something's added or removed, I'm like adjusting them as I go along, okay? So if I know it's constant time to remove something, what do we think the runtime is to just check who comes next in the line? I agree. What do we think the runtime is to just say, hey, field, size, how much do you store inside of you? I agree. How do we know? Like, oh, are you empty or not? I'm just checking a field. What is it? Yes, indeed. Okay, now, the tricky one. Remember the lesson we just learned in stack? So what do we think? What is the runtime going to be to add something to a queue? Now we have these front and back indices, so we know within this array where something might be, but we might have that secret worst case scenario hiding about. Does anyone want to take a guess? Anyone remember what we think the runtime might be? Yeah. Yes, I agree. So it's constant in most cases, linear if you have to resize. So we're hopefully starting to see a bit of a pattern with what it means to use an array to implement an ADT. Yes?
I have a question about the memory. So
Sure.
if we're always shifting like the front and back indices, won't there be like a lot of like things at the front that we just never use ever?
What an amazing question. If we just keep shifting, are we going to have all this unused space at the front and the back? Beautiful segue. Let's talk about it. So just because I think we're not only are we starting in this class to understand a bit about how we analyze the difference between ADTs and the data structures, what the kind of different patterns we're seeing in using an array versus a linked node. Here we can see another way to implement under the hood. So here we have a queue in which, let's say originally there was 4 items added into the queue, and then we removed the first item for the queue. So now we've got that empty space at the front and the empty space at the back. This is also part of why we're going to maintain those fields to know what the front and back indices are. Because let's say we add 7. Great. Now at this moment in time, if we didn't do anything, we'd have to resize the array and like copy everything over, even though we have this like perfectly valuable space hanging out at index 0 going. So what we're going to do is if we add in again, I'm just going to wrap around with my indices. And if my back index is smaller than my front index, then I know I'm in that sort of wraparound situation. And the moment those two things hit or try to overlap with one another, that's the moment that I know, ooh, I am definitely out of space in this queue and I need to resize it. So if I add again, that's when I notice, hey, I've got that sort of stuff. And so I'm just going to copy everything over, but I'll start at the front. I'll loop around if I need to. And I add that one. Yes. Just a brief way to show you again, all implementation. This is all data structure, right? Me as somebody using the queue, I don't want to know how this happens. I don't have to worry about this. This is all data structure, how it's implementing that queue ADT. Questions at all on how this wraparound happens? fun fact, this exact thing, implement a queue with an array, was the exact second round technical interview question for my first dev job at Outlook. And this question was specifically from the man that was going to become my first ever real dev lead. And we like joke about it to this day because we're still pretty close. And boy, did I bomb this, y'all. I thought I was so ready for these interviews, but something about implementing everything with our array and this wraparound thing, I got so discombobulated. He loves to tell the story how I think I got to the wraparound and I was like, oh, it has something to do with mod. And I just like, my brain farted in that interview. Life goes on. We've all been there. I tell that story every time I teach this now because it is my forever penance, I suppose, for that moment. Okay, so as you can imagine, if I'm implementing a queue with nodes, similar to the array, I will just maintain 2 pointers. So I've got a front now, and I'm going to maintain a back. And so then whenever I want to remove something, I pull from the front. Whenever I want to add something, I use the back. And we get that constant time executions because I'm at no point having to loop over everything to find something because I'm maintaining that back array or that back pointer. If I wasn't maintaining that back pointer and every time I wanted to add somebody new to the queue, I had to start at the beginning and loop all the way until I got to the back, that would be a linear runtime. But by maintaining this pointer as I go along, I'm preventing that linear runtime of build up. I'm going to get that constant runtime all the way through. Any questions? I know I'm breezing through these pretty fast. Yes. So in this case, I'm removing because I know exactly which thing to remove from. It's always going to be the very first node in the list. So it's going to be the node that front is pointing at. So I only ever have to do the like, okay, current, hold on to the rest of the list, remove this, front, skip it kind of thing. Yes. Good question. Any other? Yes. So great question. Is there any reason to ever use arrays? And I will tell you the really annoying thing is actually you will find in industry, almost no one ever uses linked lists. They almost always use arrays. And the really annoying part of this is conceptually, we've been talking about this constant runtime, but the practicalities of arrays end up overwhelming the performance of linked lists. Because if you remember that like in memory, how like a linked list nodes could be here and here and here and here, and they're all over the place. The inefficiency of the memory finding those nodes actually ends up climbing worse than just the contiguous blocks of memory. So you'll find that for the most part, we actually use arrays under the hood. But you are absolutely correct in that it is painfully obvious how much better linked lists are from a pure theoretical analysis standpoint. Yes. This is also me because I think linked lists in the industry do have kind of a bad rap. People just like arrays. We're very comfortable in arrays. The computer's built in arrays. We're all a bunch of engineers. We're obsessed with arrays. We can't help it. And I think in a lot of situations, linked lists actually do end up becoming a better choice. People are just afraid to drop pointers, as it turns out. We've been there. Great question. Okay. More real-world examples. Unfortunately, we don't have time for this design discussion, but I'll let you read it on your own time. There's one more ADT that I want to make sure that we understand because this is the one, man. This is the ADT that we will not shut up about for the rest of this quarter. You probably know it as maps. We will continue to refer to it in this class as dictionaries. And it is the idea, every programmer's best friend. It is the idea that we now have a structure that has 2 pieces of information for every singular entry. You probably did it as either a hash map or a tree map in 143. This is how I like to visualize it. It is an unordered set. So that's why we have this like sort of oval, I think of it as a blob with a bunch of little pairs floating about in it. So this will not maintain the order as you put things into it. However, really the point of a map is great lookup. You can think of a map as a dictionary, and you can think of it as like an actual dictionary. Do you remember once upon a time there were these things called books, and you like took them off of a shelf, and then I said, look up a word in a book, and then you like opened this book to the middle, and you asked yourself, is the word I'm looking for earlier in the alphabet? And then you looked at the front part of the book, and then you kept looking in the book until you found the word, which was the key, to the value, which was the definition, the thing you were looking for. So a dictionary is this set of values that is not ordered according to how you put it in, but we will find throughout the rest of the quarter is ultimately instead ordered to optimize for lookup. So in the dictionary, it's alphabetically ordered because that should hopefully be more optimal lookup. As opposed to, I don't know, random order, we'd be all struggling, right? So put is the act of adding a new one of these sets to the dictionary. Now, keep in mind the key to dictionaries is that keys must be unique. This whole thing falls apart if one key can represent multiple values. So if you put something into the dictionary, the very first thing the dictionary is going to do is going to check, does that key already exist? If it does exist, you're going to replace it. So keep in mind, if you put a duplicate into the dictionary, it'll overwrite. That's how it's supposed to work. Get, tell me the key, I'll return you the value. Contains key, tell me if this key is somewhere in here. So technically put is calling contains key under the hood every time it runs. I will tell you why this is important. And then remove aside. So again, implementing a dictionary with an array. Now you can see inside of our little array elements there, I've got 2 items per entry. So in this scenario, the keys are the letters, the values are the numbers. So you can imagine like maybe this is a scenario where like my dictionary stores, you know, like give me the number like sequence in the alphabet for this given letter, something like that. So in this situation, in order to, let's see, are you going to let me? Yes. Let's see what my animations are doing. Okay, ignore my animations. They're a hot mess. But in this, what's going to happen is in order to tell if I have a duplicate, because things aren't ordered in any particular way, I have to loop over everything in order to see if there's duplicates. And so we're going to end up with this linear runtime because we have to look at everything in the dictionary to determine if this is a duplicate before we add anything new. Same thing with get. So what we're doing is we're sort of starting at the beginning of the array and we're looking at each one of those keys and we're saying, hey, is this the key I'm looking for? No. Hey, is this the key I'm looking for? No. Let's say in that last scenario, that E, I'm going to start at index 0 and be like, hey, is this an E? No. Is this an E? No. Is this an E? No. No. Up, there's my E. And so in order to accomplish that, I had to touch every single thing in that dictionary. If I had to search through everything in my collection in order to accomplish my task, that's a linear runtime. If I had 100 things in this list, I would have had to check all 100 things to make sure it was in there, right? Now, here comes back to this sort of best case, worst case situation. If I am trying to add something into the dictionary that is already in the dictionary and just so happens to be the very single first thing I look at, I don't have to keep looking to find everything else in the dictionary, right? So I sort of end up with instead this constant time if the thing I am looking for happens to be at the very beginning. I end up with this linear runtime if the thing I'm looking for isn't there or is the last thing that I am looking for. And again, we kind of get this situation of best case, worst case scenario. We're like, well, it'd be really convenient if that thing I was looking for was the very first thing in the set. It would be very inconvenient if the thing that I'm looking for isn't in there because I would have to look at every single thing in order to confirm it's not in there. And that's where we get that linear runtime for the worst case, constant for the best case. Yes? What if the array is full? And that's great in this situation. So in the big O analysis, if the key is the last one looked at / not in the dictionary, you can put there. If the key is the first one looked at, then I'm not going to have to grow the array. I'm just going to replace it. So I'm only going to have to grow the array if the array is already full and this is the very last thing I am going to look at. So I would have already been in the linear time run at that point anyway. But what's annoying, and we're going to talk more about this, is that you might be like, well, Casey, I probably had to look at every single thing in the array to determine that it's not in here. And then I realized that I need to grow the array too. So then I got to copy everything over as well. Isn't that like double N, like 2N? And the answer could be yes. We could talk about how you could optimize it. But in this land, we're going to sort of treat those factors of n all within one complexity class. So 2n, 1n, 10n are all going to sort of be treated like the same complexity class. I'm going to talk about that, I promise, ad nauseum this week. Yes?
So just to clarify, so for the worst case scenario for size, it's constant because it's keeping track of the size of the dictionary, or?
Thank you. Yes, the size is always constant because what that code is doing is just returning the value of a field. And so as long as every time you add something to the dictionary, you increase that field, and every time you remove something from the dictionary, you decrease that field, then you never have to incur that linear runtime to count up everything. So that's why that size method is always constant, because all it's doing is literally just returning the value of an int field. Great question. Any other questions? Hopefully we're starting to get a little bit better sort of like understanding of where that constant versus linear is coming in. As you can imagine with nodes, okay, fine. We're sort of creating nodes, but we still have to look through everything. And so we end up with this very similar runtime where if the thing we're looking at isn't found, then we have to check through every single node to find it. We get that linear runtime, but we don't get any improvement in the linked node situation for this, unlike the other ones where the list node was always far superior. And this one's exactly the same because we're already have to search through everything. We're already going to incur that linear runtime no matter what. Great. Okay. All right. I'm going to take a moment here and look over, see if there's any questions in our, on our Ed board post. Does anyone have any questions about this before I dive into our next big topic? No questions for you? Yes.
Like the node implementation.
Mm-hmm.
Would there be a way to like optimize it so that it's
Is there a way to optimize it so that like we don't get that weird, like sort of like the nodes are all over? So where things get stored in memory is totally owned and operated by the operating system. And actually, if you were to say, go on from this class and work in operating systems, the people that work on computers, that's what they're trying to figure out all the time. How do they optimize that to make those sort of placements of memory better and better? But that's the operating system's job, not our code's job. Now, we can write our code to optimize it a little better, but the only thing we can really do with our code is use arrays instead of nodes. But if you want to solve this problem, go join Windows, or technically my team, I work on operating systems. Chrome OS, I know everyone's favorite operating system. Oh no, don't tell my bosses we all laughed at that and that I definitely set that up because I know it's a joke. Just kidding. I know. It's okay. Hey, 50 million education users, y'all. We went to one-to-ones because we have $100 laptops. Never forget. Okay. Oh, man. They should fire my ass so hard. Okay, so we've talked about a lot of different ADTs. Let's get deeper into how we do this mathematical analysis. So we talked a bit more about complexity classes. Hopefully we've seen them play out in some ADTs a bit more. But in this situation, I gave you some kind of examples, like, oh, if I have to loop over and find everything, that means I'm going to touch it. Or if I have to grow my array, I have to kind of drag everything down. Or I'm giving you that like nested situation, like maybe I have kind of two loops. But that was all just like us sort of looking and identifying patterns. How do we systematically and mathematically go from code to the mathematical formula for how the runtime is impacted by n? Meaning, how do we go from code to this idea of big O, this asymptotic analysis that we're going to talk about? So we had some basic patterns. This is what we're going to do together between today, Wednesday, Friday, and then I guess actually Monday and Wednesday again next week, is we're going to start going on this pipeline to figure out how to analyze code. So the first step is what we're going to do is we're going to take our actual lines of code and we're doing something called code modeling, and we're going to transform that code into an algebraic function that relates the number of instructions in terms of how many things are stored in the data set, i.e. n. Then, once we have that mathematical function, and you can see in our little sort of pipeline here, like once we go from code to something that looks like this then helps us get to that sort of more generic big O notation using something we're going to call asymptotic analysis. And you've heard me a couple times sort of express things like, we're going to ignore those constants, or I'm going to show you how like at certain scale, these things are going to drop out. That's all in this part of it. For right now, we're just figuring out this piece, which is how do we go from code to this actual sort of algebraic expression. So, code modeling, the process of mathematically representing how many operations a piece of code will run in relation to its input size. I like to think of it as just going line by line and counting. And now here's the kind of annoying thing. Some things, quote, count, and some things kind of, quote, count differently. And so we're doing this situation where we're going to kind of systematically count how many basic operations are happening in the computer. If you are like, Casey, what are we actually counting under the hood here? What we are trying to do is we're trying to get roughly close to counting the number of assembly instructions that we're sending into the actual processor, but at a higher level. And if you're like, I don't know what that is, you don't need to know what that is for this class at all, but I'm happy to explain it to you if you want to know what's actually going on at a later point. What we are going to count is we're going to count anytime we do any sort of basic math. Anytime we add something, subtract something, divide, any of that stuff. Anytime we store something into a place in memory. Anytime we return or send a piece of information somewhere else. Anytime we establish a variable or access a variable. So this is like storing something, making space for something, pulling something out of that space, sending something to another place. These are the basics of what code is doing, right? The basics of combining data, storing data, moving data around. That's what we're counting. And that's why I said we're getting close to that sort of underneath the hood, just like the foundational instructions of what we're asking our computer to do. So really, this is a whole step where we're asking you to take a look at your code and start to think about it on a whole nother depth level than we've probably asked you to look at before. It will take a while to understand this. But this is the thing that you'll find trips people up, especially in interviews, because we don't really think a lot about what our code's doing under the hood. And we can have lines of code that's just like, we called arrays.sort. We don't know what it's doing, but it did something real fast. And in this now situation, we're going to ask that you really start to pull apart every single piece of code and think about what's really being asked of the computer. The other things that we are going to count is anytime we call a function. That's us telling the computer, hey, move your attention from over here to over here. That counts as an instruction. And then you sum up the total runtime in the body of that function. That's probably a bunch of these things. Then there's a bunch of conditionals. The act of comparing two things. Maybe you do some math on this thing and some math on that thing, and then you compare those two things, and then you enter the if statement. That entering the if statement, that also counts. Loops. Here's the annoying one. In this situation, we're pretty much just going to count how many times that loop runs. That's what we're counting in that situation. Let me give you a specific example because I think this makes a lot more sense. Let's look at some code together. So the way that I will do this is I'm going to kind of start at the top. I'm just going to go from the top to the bottom. So right here, I see I've got an assignment. So I'm like, ooh, okay, there's maybe like a +1. I'm like creating some space. I'm putting something in it. Maybe here's another one. Then I get to this while loop. I see there's a sort of comparison in here. Maybe that's like a +1. And then in here is a bit of math, +1. Here's another bit of math, +1. Then I store that, +1. Here's a bit of math, +1. Here's an assignment, +1. And so I get some amount of stuff that's happening within this loop. Let's see, how many did I count this time? 1, 2, 3, 4, 5. Let's see how many I did. Okay, there's 1. Yep, 1. Okay, so I counted that as 3. Looks like I did count that as 3. Here's 1, here's 2, here's 3 on that line. Here's the 2 on that line. So there's that addition and then that assignment. So what's happening is inside of this while loop, we can see there's this +3 and this +2, and then there's this +1 maybe for comparison. And that's going to happen a bunch of times, right? Every time that loop runs, these two things plus this comparison's happening every time. And then finally that return, like I mentioned, that's a +1. So does anyone have any questions, at least at this level, before I show you how I sort of sum this up? Like, are we okay with the idea that I sort of pulled out those +1s there for that basic level of operations, meaning some addition, some accessing of memory, some making space in memory? Any questions as to where any of these ones, this 3 or this 2 came from? So now we got to figure out how this loop influences it. And so I added up everything in the loop, which is this 2, this 3, and this 1. So that's where I got that 6 from. And now I can see, and I did this on purpose, we need to do this in terms of n, right? And we can see how many times this loop is going to run. The loop runs n times because I starts at 0, and it's going to go while I is less than n, and each time we run our loop, I counts up by 1. So if n was 3, I would be 0, 1, 2, 3 times. If n was 5, I'd go 0, 1, 2, 3, 4, 5 times. If n was 10, I'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So that's where I'm getting that n factor because it's part of this loop counter. Any questions as to how I pulled that term of n in? No? So my final code model, my code function to represent this is 6n, which represents the instructions coming from the while loop, plus 1, 2, 3 of the little items that are outside of the loop. And I end up with this nice sort of algebraic function here. Taking a quick peek at this algebraic function, does anyone want to guess which complexity class this code falls into? Oh, I love all the hands. Sure. Big O of n, absolutely, because this is a linear algebraic function. Aha, we're heading in a direction, yeah? Any questions on how I got 6n plus 3? Yes?
If it was I equals I plus 2, would that be like 3n plus 3?
Ooh, if this was I equals I plus 2, so that would mean I would go, if I say had an n of 4, and I had I equals I plus 1, it would go 0, 1, 2, 3, so I'd have 4 times. If I did I equals I plus 2, I'd go 0, 2 times. So I'd run half as many times. So what you would end up having is, you're right, I'd have like 1 over n, and so instead of 6n, that would be 3n. Because it would impact how many times the loop runs. But you're absolutely starting to think of this in the right way. How do we figure out how many times the loop runs? Great. You try. Take a few minutes, talk to the people around you. Also be that cool friend. Introduce yourself. We need partners in this class. Talk about this, and before we leave class today, I'm going to show you the example. Okay, let's see if my animations are good. I'm going to give you the first layer here. I'll let you keep figuring out whether these two. So, for example, that one comes from there, that one comes from there, that comes from there, that comes from there, that comes from there, that comes from here, and then from here. This comes from 1, 2, 3, 4. 1, 2, 1, 2, 1. Hopefully that kind of explains where those come from. Okay. Unfortunately, we are out of time, but does anybody want to share with us what they did anyone get to a final answer or want to be brave and share with the class? I'll take a few different answers. Yeah. 9n plus 4? All of it by n? Yeah, okay, I like it. Any other one else? I'll take a few. Yeah, in the back. Okay, wait. I want to hear in the back. Go for it. 9n squared plus what? 3n plus 3? Yeah? I love it. Okay, let's see. Who else has got one? Way in the back. Let's hear. Plus what? Plus 3? I love it. Okay, yeah, another one. 27 squared plus 5. Okay. You know what? Taking a look at all of these answers, what do they all have in common? N squared. So guess what? You're all correct because that's technically, here's where, let's see, my answer ended up. There we go. That's where mine ended up. Hey. But as long as you got to n squared, you did it right. Come back on Wednesday. We will dig into this in more detail. Thanks for going on the journey, everybody. We'll do one of these for warm-up on Wednesday, for sure. Mm-hmm.